Welcome to Make Visible, the podcast shining a light on complex chronic illness. I am your host, Emily Kate Stevens. Welcome back. This week, I have the pleasure of bringing you a conversation with Dr. Michal of the Centre of Gynopathology and the Tal Research Group at MIT. Her team there is responsible for investigating the pathologies, effects, and connections between infection-associated chronic conditions, as well as making serious inroads into our understanding of and relationship with menstruation science. Let's start off by talking about what you and the group at the Centre for Gynopathology Research have done there at MIT this month.
So we have decided that menstrual taboos have really done us nothing but a major disservice, and that avoiding the topic of talking about menstruation, having women not know if what they're experiencing is or is not normal, is or is not detrimental to their health, how to expect menstruation to impact perhaps chronic illnesses that they already have and symptom flares and such, or just how to expect in terms of the amount of pain that they might experience per month. What we have decided is necessary under the incredible inspiration and drive of Linda Griffith, who's the director of the Centre for Gynopathology Research, is that this really needs to be its own scientific field, bridging engineering and biology, where what we can do is develop a scientific language. So what's been missing, if you think back to where breast cancer used to be, that it was the more shameful of the cancers and people said breast and thought boob, whereas today people are thinking, oh, is it estrogen receptor positive? Is it triple negative, what kind of breast cancer? And there's a whole scientific language, and renowned doctors and scientists who work in this field. That's where we're hoping to go with menstruation science, to develop a vocabulary so that you don't say the word menstruation and people think gross, but that you say the word menstruation, people start to think, okay, are we talking about heavy menstrual bleeding leading to iron deficiency anemia, and thinking about menstruation in terms of the impacts of health, which are tremendous. And some of them can be lifelong and will last long after you've even stopped menstruating. So it's a really key part of many people's lives that we need a much deeper understanding of.
So it's about trying to bring it more openly into a conversation between people, but also trying to bring much more of a focus into using it in medical advancement. And I was reading that you are, because obviously a lot of your work, you have brought up and this is another section that we can talk about, the sex differences between susceptibility for chronic illness, the way that it impacts people. But you've got a lot of different strands here. But I was reading that there are certain things about menstruation that are not really talked about, but the implications that it might have if we had greater understanding of it, it's simply in things like wound healing. And the fact that I had no idea until I was reading about this, the fact that we're so limited in terms of the female-centric research that has gone on historically. And even then, a lot of it in mouse models where mice have, am I right in thinking they have two uteruses and they don't bleed naturally? Is that what I read?
They have, so their uterus has two horns. Yeah. So it's this essentially like a double uterus model, which can sustain multiple births regularly, and they don't bleed naturally. There's only one kind of mouse that naturally bleeds. But our standard mouse models do not normally bleed. There is a way to induce menstruation in a mouse model, but it is not natural.
This is what we've been using historically as the basis of some of our research into not just female sort of reproduction health. We've been looking at it related to various different diseases. Is that right?
It is. No model is perfect, right? Every model has flaws. There's a lot that we learn from our mouse models, and mice do cycle in terms of, they do go on this hormonal roller coaster of estrogen and progesterone and prepare for pregnancies differently than we do, but with a lot of overlap. And so there are things that we can learn about their hormonal roller coaster that apply to us as well on a different scale. Obviously, our hormonal roller coaster is spread out across an average of 28 days, and theirs is spread across 4. So it's a condensed version of ours. But I think the biggest thing I want to say is we had this big launch event, and we invited Hilary Critchley from Edinburgh, who's an absolute legend in really driving forward our understanding of heavy menstrual bleeding and what's happening. And just like you've probably heard for pregnancy, the event that everything goes right and you end up with a healthy live birth, that's kind of the miracle, right? That's so many things needed to go right for conception to happen and to result in a healthy baby. So on a smaller scale, 400 times in a woman's life where she's going to have experienced menstruation, for the bleeding to be a normal amount, not heavy menstrual bleeding, there's a lot that needs to go right similarly. And so you have to tighten up these blood vessels that provide the blood supply to that lining of the uterus, that inner lining called the endometrium, which is what really kind of grows and sheds every month. And if you don't cut off the blood supply properly, you're going to have way too much bleeding. And so there's this whole intricate interplay that needs to happen between your vasculature and your blood flow and your uterus and the lining. And this is all driven by that hormonal roller coaster. And so what Hilary Critchley made really clear is that in the past, people used to try to look at models of, let's look at that. If we give a ton of progesterone to try to mimic the peak, what would happen? Or if we give very low levels of progesterone to mimic a trough, what would happen? But her big advancement to the field is to say, what has to happen is you have to hit that high, and then you have to have that withdrawal. What's really driving these processes is the starvation of progesterone after you've had a high amount. So it's that on the roller coaster where these critical events need to happen in order for a healthy menstruation that is not going to deplete you of all your iron. I mean, she's telling us about scenarios where it's essentially like somebody donating a pint of blood every month. I mean, that would make the healthiest person fatigued and have major health impacts. I mean, that's just not the normal amount of blood that you should need to replenish.
That's what was happening to me. I've had long COVID for 5 years, and I was bleeding 0.5 litre of blood every month. So whatever else I was doing to try and bring myself back into balance, as you say, that's not
that would
normal.
Do anybody in. That's not normal. And that would do anybody in. And that's where I think, especially with long COVID and with these other infection-associated chronic illnesses, this is where the vasculature comes into play. Because if you have leaky vasculature, if your vasculature doesn't have the structural integrity that it should have. So if you imagine a tube, right? And normally as you constrict this tube to cut off the blood flow, for every half that you reduce it in size, that's a 16-fold reduction in blood volume that's going through because of how tubes work, right? So the problem is that if your tubes are floppy, and we know this, we know in long COVID, there's multiple problems. There's both the vasculature is floppy and leaky, but also there's this microclotting that's happening. So the blood flow through is not normal. And there's these microclots that are impacting. And then when you have that scenario going on in this vasculature that needs to constrict, and now you have a problem with the integrity of that, then of course you're going to have heavy menstrual bleeding. And that's going to in itself have all these other impacts for your health, because now you have to overcome this tremendous depletion of iron and red blood cells. And that iron deficiency is going to really do you in. And it's going to be really, really hard to overcome. So there's going to be an impact of your vasculature has so many impacts on you. And if your blood flow is off, it's going to impact a lot of things.
I mean, we've sort of jumped. We've jumped so far in already. But actually, that conversation correlates with a study that you were involved in where you were looking at Lyme disease and the multiple gynecological conditions that actually stem from Lyme disease. And I think heavy menstrual bleeding,
or abnormal uterine bleeding is the other term,
was one of the primary gynecological conditions that you found to be prevalent in Lyme disease, along with miscarriage, fibroids, and
endometriosis.
Is that paralleled, do you think, in long COVID?
What we know at this point about long COVID is that there are some important parallels with infection-associated chronic illnesses that we've known about for a longer time, like we see with Lyme and like we have with ME/CFS. But there's a two-way street here. And what we also know from women who have endometriosis is that they were more likely to get long COVID. And so there seem to be these very, very important interconnections between infection-associated chronic illnesses and gynecological diseases that we have done a tremendous disservice by not trying to understand what this two-way street is between these gynecological diseases and the infection-associated chronic illnesses, and to try to understand why either one gives you an increased risk of the other. So either way, long COVID would have given you an increased risk of endometriosis. Endometriosis would have given you an increased risk of long COVID. And the chance that you would have both is much higher than the chance that any random person off the street would have either one.
Okay, so let's take this conversation right back to what you do at the Tal Research Group, which is you study the connections between these infections and chronic diseases. You are trying to improve the diagnostics and treatments for them, but you're also looking at the prediction of them happening. And is that partly what you're talking about here in terms of, you were involved in a study, was it last year, that looked at a lot of the different comorbidities in long COVID? So are you suggesting that there are certain parallel conditions, certain comorbidities that you would use as a predictor of people developing post-infectious chronic conditions? Or are there other things that you are looking for in terms of that prediction?
Okay. I want to address all of it, and I think I need to do it in pieces. So I want to start with what we do in the lab, and then I want to go into some key questions, and then I want to come back to how do we build these predictive diagnostics. So starting with what we do in the lab. So in my lab, we haven't yet given up on mice. We keep them around because they are also quite useful when you use them for things that they are relevant an important model for. Lyme disease is special because they're one of the main vectors of Lyme disease. Lyme disease is a natural infection in the mouse model. And so we can study this bacteria in a host that it has evolved to infect and establish a chronic infection in. And we can compare different strains of mice for how they respond to that, to look if we keep the bacteria the same and the infection is the same, but we change the immune system and we change the genetics. How does that impact the outcome and which systems are affected? So our mouse model is very useful for getting into the mechanistics of what these bacteria are actually doing in a way that we can pick and prod and really look very deeply at these different aspects. We also have a huge human clinical study going on, the largest at MIT. I'm very proud of this. So this is the MIT Maestro study, and a major part of my lab is working on that. So we have a clinical study nurse, Siri Kim, who most of the people who would have participated in Maestro would have met. And then we have a lot of other people in my lab who work on this, either helping out with the clinical study or biobanking these samples, or then analyzing these samples or sending them out. And we work together with many different companies, both in terms of the profiling we're doing during the visit, as well as subsequent profiling that we're doing afterwards.
So you're looking at 300 participants for that study,
yes.
Is that right?
Yeah. That's the goal, and we are well on our way. And we are so tremendously grateful for everybody who's participated, because we haven't been able to compensate people, and people give so much. And what's really heartbreaking is that so many of our participants have told us that they have lost hope at this point for themselves. And they're participating because they're trying to help us figure this out for other people, because they just want to spare other people from experiencing these really, really dreadful, debilitating illnesses that have stolen so much from them. And it's just, it is so unbelievably moving, where we have people who have been left with so little and they give so much to really try to help in any way that they can. And we are learning so much from each and every one of our participants. When they come in, so first of all, they've answered a huge burden of different surveys, and then they are doing a whole suite of neurocognitive assays to try to understand neuronal impact, neuroinflammation, and we look at dysautonomia.
The first one where you're looking at the brain is them doing testing, sort of that neurocognitive type testing, rather
There's
than
a
the
suite
electrical.
of different tests. So
Okay.
there's eye tracking to see
That's
what's
fascinating.
happening. It's very fascinating.
So the eye tracking is to determine whether people have a problem with their neurocognitive processing rather than their eyes. Is that right?
Yes. So I'll tell you, the eye tracking piece started because we were hearing, originally this really started from our Lyme research. And there's a philanthropist who was supporting our work who was thinking with us about the research that we were doing. And what we were hearing from people is that there were college educated people who had never recovered from Lyme who were now not able to read. And so we had this question of, okay, can they not read because something has gone wrong with their vision? There's lots of common, you could have double vision, so is this an eye problem or is it a brain problem? And working with this company, Right Eye, which allows us to do this eye tracking that can distinguish those processes. And so we can really tease apart here, are there problems that are specific to the eyes or are these problems in the brain? And then we can compare that to other measurements, like you mentioned with the electricity. So we have an EEG cap that they wear, and that can look at voltage coming out of the brain, where we can do, similar neurocognitive tests, but then look, okay, are we seeing lights on, lights off, or anywhere in between?
So that's looking which regions of the brain are being stimulated.
Which regions of the brain, exactly.
Wow. Just to clarify, the Maestro study, which is the mucosal and systemic signatures triggered by responses to infectious organisms, that is looking both at chronic Lyme and long COVID. Have you included MECFS patients in there as well?
We would love to, and we are trying to. And I have to say, half of long COVID at this point have MECFS. And so that is reflected within our Maestro study. And we have been working really hard on getting additional funding to support bringing in people with MECFS. And one of the research scientists in my group, Beth Pollock, has actually been working really hard on that and is trying to bring in a subset of people with MECFS who have MECFS not from long COVID. So that is something that we're working on expanding into. But at this time, the Maestro study itself is focused on this comparison between acute Lyme and then following them over recovery or not recovery compared to people who have had Lyme and recovered or had Lyme and didn't recover, and they're over a year past their infection and haven't recovered, versus had COVID and didn't recover over a year past their infection.
Okay. And have you done that also with people to mirror the Lyme? Have you done that with people who have acute COVID?
We really wanted to. MIT was like, what? Now you're talking about bringing in people who are contagious actively with COVID? No. So at the time that we were proposing that was completely shut down, and appropriately so, as we're talking about a place where we're bringing in people who we're trying to protect from catching anything additional than what they're already dealing with, and we just didn't have a way to bring in to this space people who actively
infectious.
Yeah.
And then within that study, and this study almost ties together so many of the things that you have studied or that you continue to study, because you also then do the Nasoline test. So you're looking at that orthostatic intolerance. And Two things that I haven't heard of people looking at in this situation before is this skin barrier testing and hypermobility testing. So it's bringing in that kind of EDS element to these conditions that possibly have not been looked at in parallel before. Can you tell me about those two sections of the testing?
Sure. And I can also tell you that we can then even more deeply characterized also in our mouse model. But this is something that we've been interested in. And you had mentioned a study that we collaborated on from Mayo Clinic, where they reported on all these comorbidities. And one of the comorbidities that they reported was increasing significantly, especially in women, was EDS and hypermobility spectrum disorders. And I mentioned a research scientist in my group, Beth Pollock, who has a strong interest in ME/CFS, but also in the less studied pathologies of the infection-associated chronic illnesses, and specifically this hypermobility EDS connection.
You just said that she's interested in the post-infectious. Do we already have that type of EDS classified in post-infectious?
So I didn't say post-infectious.
Sorry, infection-associated.
And I just want to clarify that, because one of the things we're trying to do in Maestro is strip away some of these assumptions and just look at everything. And so one of the things that we actually don't know yet is, are we looking at a post-infectious disease or not? And so I just want to, while we had earlier said about people who were actively contagious with COVID or not, I'm not sure yet. We're looking and we're asking one of the things we're doing is this deep pathogen profiling. And we're trying to ask, is there any Borrelia still there? Is there any SARS-CoV-2 virus still there? So I just wanted to clarify that. But yes, in regard to your question, do you get EDS after developing these infection-associated chronic illnesses? That's one of the questions we're trying to understand. Certainly that earlier publication would support that there's evidence. And there have been some other reports to show that there is definitely a connection, again, a two-way connection. Does EDS put you at higher risk of infection-associated chronic illnesses? Does hypermobility put you at higher risk? And so hypermobility that we generally think of as benign, but is one of our big questions. And also the other way, if you had an infection-associated chronic illness, are you now going to develop a hypermobility that you weren't born with? And are you going to develop EDS that you weren't born with? So these are questions that we're actively trying to look at both in Maestro, but also in our mouse model of Lyme disease, where we'll publish this probably later in the summer, but we have a strain of Lyme that are developing hypermobility.
Wow.
Who wouldn't develop hypermobility on their own without the infection.
Wow.
Yeah.
When you say you have a strain of mice, so does that suggest that there's a genetic component?
Possibly, because it's not happening in other strains. But I do want to emphasize that in their genetically identical counterparts who are uninfected, they're not developing this. So it's not just the genetics, it's the genetics plus the infection combined. Yeah.
Where you're seeing this overlap, it is where you are seeing this overlap of so maybe one without the other would be all right.
Exactly. And that's exactly what we see. One without the other is all right. And so we have other models that we can infect them with Lyme and they're okay. And we have other models who are genetically identical and uninfected with Lyme and they're okay. But now you take the combo and that's where you have the problem.
That is fascinating. I've read you say that long COVID is exactly like Lyme disease in some respects, and clarifying that it's a different pathogenesis. But one of the things, and obviously this is what you've just said, that you're doing pathogen profiling, or did you say you're doing immune
we're doing deep pathogen profiling and immune profiling. Absolutely. And so yeah, I want to address that because some people definitely took issue with my comments there about the similarity and the tremendous overlap in clinical presentation. And so I think the point that I was trying to make there is that if you hear from somebody who's experiencing infection-associated chronic illnesses, and maybe now we're touching back to some of these comorbidities, there are a constellation of comorbidities that they are describing and experiencing that overlap tremendously across the infection-associated chronic illnesses. while they may be much more rare in other swaths of the population. And so if we think about comorbidities with any illness, like let's think about cardiovascular disease and the different comorbidities that you have around there, you have things that are much more likely to come together than to occur just to any random person off the street. And we have the same picture happening in the infection-associated chronic illnesses, where there are these different manifestations, outcomes that look very similar. And so the clinical presentation, while extremely diverse within long COVID and within chronic Lyme, you have an extremely heterogeneous presentation that could show up in these different, there are different things that could go wrong, but the same things that go wrong in chronic Lyme also go wrong in long COVID. And so we are trying to, in parallel, investigate the infectious driver of this, as well as kind of define better biological networks, because it may be that there are some shared features between some people with chronic Lyme and long COVID, that maybe what they have happening is actually that they've lost the ability to tolerate microbes that live with them, or they have some kind of allergic response happening that maybe they could benefit from the same treatment if we identified them as a network. And maybe it would be more important to understand what's happening to them on the disease level, what's the driver of the disease, as opposed to the infection that got them there, versus people who actively still have presence of SARS-CoV-2 infection somewhere, some kind of reservoir of infection, in which case they would probably better benefit from treatment of that ongoing infection. And so this is where it's really important to just look and see what is going on.
Yeah. So you're saying that instead of a viral reservoir or viral, maybe even reactivation, there's something that's stuck in the immune system that it's triggering.
Saying that I know which one it is, I'm saying
That's
it could be. These are all possibilities that we're investigating simultaneously. The approach we're trying to take here, and what we like to say about Maestro, is that the idea here is just to leave no stone unturned. And what we're hoping to get out of this is to essentially write a textbook on the infection-associated chronic illnesses and what to look for and what to track, how you could follow that, how you could diagnose it earlier, and what you then want to screen for. And this could be really, really, really critical in educating a new generation of clinicians who are seeing something that science hasn't really provided them yet with the information and the tools to manage and treat these now very common illnesses.
Do you think it's likely, I've spoken to various people recently who have suggested this, do you think it's likely that you actually find there are multiple of these facets? So there might be people who still have the virus active, but there might be people whose immune system has got stuck. There might be people in whom it has triggered another condition such as mast cell activation, but these are all different pathways that have come not even necessarily from the same pathogen, but there are parallels between the conditions and there are differences within each of the conditions.
I'm almost certain that we're going to find some and some and some. And that what we have been calling long COVID and what we have been calling chronic Lyme are actually umbrella conditions that include multiple different subsets. And that's where the compare and contrast approach that we're taking is very important to us, because we're trying to understand which of the subsets, for example, have some kind of immune reaction that would benefit from the same kind of immune modulation, as opposed to which subsets have some kind of infectious agent or some kind of microbe, whether that be now a herpes virus reactivation or whether that be the driving infection, but where they would benefit from some kind of antimicrobial, whether that be an antiviral or antibacterial. And so it's really, really, really important to distinguish these, because for some, if it's an immune driver, they're going to benefit from being looked at together regardless of the infectious trigger. but getting lumped into, okay, these people are all having mast cell activation, and let's calm down those mast cells and let's see how far upstream we need to go in order to do that, versus actually, is there an ongoing infection that we need to directly take care of?
Absolutely fascinating, isn't it? And within the community, there are so many different reactions because some people find it really offensive that there is a suggestion that you might be able to treat them without removing a viral persistence. And this idea that it could be all different would play into that, the reason that some people have managed to recover by doing breath work because they have reduced their stress bucket or however you call it, versus the people that whatever they seem to do, whatever treatment they seem to, help apheresis or whatever they try to do to manage certain aspects of it, they've not been able to get better.
So what I want to say is I once had a very interesting argument with somebody about this topic exactly, because I think she had taken offense at a comment that I had that this all essentially stems back to immune dysregulation, which I stand by, because what I meant about that is your immune system is tasked with clearing offensive microbes and infections, and both in killing that microbe and preventing it from replicating, and or if it's a good microbe that's just supposed to live with you, tolerating it. So the immune system has already been tasked with controlling our microbial populations. And if the immune system is failing in doing this, whether it be that there's an ongoing reservoir of infection that the immune system has failed to attack and root out and clear, that is inherently also an immune dysfunction. So from my immunologist view of the world, all of this stems back to immune dysfunction, whether it's that you couldn't clear the infection that other people were able to clear, or whether it's that you did clear the infection, but there has been something about the immune response has gone off the rails and your immune system is now out to kill you. From any of those directions, in my mind, they all stem back to immune dysfunction at some level or another. But I think it's extremely important to figure out what is driving that immune dysfunction, because there's not one blanket answer that could cover all of these people. And we have so many people who have not been able to recover. So I think there's an incredibly pressing issue that I know everybody in my lab feels, that this incredible purpose and this pressure to help give people answers who are just unbelievably ill and really haven't been given anything there's no approved treatments. They have nothing. And so they're trying different things that they've heard of, but I feel like it's on us to provide these biological networks to figure out. So this is maybe where we can come into the predictive diagnostics. So what we're trying to do is essentially build these illness trajectory maps. This isn't about the comorbidities so much as this is asking, when you have an infection, why doesn't everybody bounce back from that infection? Why do some people go on to become increasingly, progressively, debilitatingly ill? Why does that skew female? Are females and males having the same disease or not? This is where we come into those sex differences. Those sex differences are really important. Age matched, males are more likely to die from flu or COVID than females. But if they survive that initial infection, they're less likely to then have chronic illness from it. And that is counter to this scenario in females who are less likely to die from the acute infection, but more likely to have chronic illness from it. And so why is that? Are the same factors at play? Is there something we could learn from the male playbook here? Is it testosterone? We have so many questions, but in terms of building these illness trajectory maps, what we're trying to say is how early into your infection or in your response to infection can we probe your immune system and ask it, are you responding in a protective manner? In which case, this person's going to recover. This is going to be a nothing. They're probably never even going to think about it again. No worries. Or are you not on track to recover? Immune system, are you responding in a catastrophic way? And then in that case, we can start to ask, okay, what flavor of catastrophic? But the question here to the immune system is, Are you doing what you need to be doing, or are you going to bring the house down? And that's a question we haven't been asking our immune systems previously.
Does that relate to when I've read about you talking about our IgG and our IgE response? Can you just explain the differences there?
So I think in the COVID days, I think everybody got to hear about antibodies, these proteins that you make to fight infection. They are specific to particular features on a given virus or a given bacteria. And some of them are against features that are shared across many bacteria or many viruses. And the way that we have always done antibody tests clinically in the past is that we have asked the immune system a yes or no question. Have you ever seen this bug before? Yes or no. And we essentially count IgGs against a particular feature. And that's the yes or no. Over a particular count is yes. Just any IgG. Doesn't matter which kind of IgG. This is an assay that was brilliantly developed in the 50s and refined in the 60s. And that's what we're still running today in 2025. And we are not limited by the tools that were available in the 50s and 60s today. And so today, you could take just about any immunologist today, and you could ask them to run for you a panel of all your different antibodies, and they could do it because we have the technology today to look very deeply simultaneously at different kinds of antibodies. And yet we have focused so much of that technology. If you think about antibodies like a Y, so there's the part of the antibody that binds the feature, and that may be very unique to a particular virus or shared across viruses. And there's what I call the business end of the antibody, the stem, which is what interacts with the different immune cells. And so it can bind to different immune cells and it can drive different effector functions of the immune system. So you could drive allergic type responses, or you could drive in, essentially it's like thinking about, is this kind of antibody going to bring in a little SWAT team to very quietly take care of this pathogen? Or is this antibody going to bring in an airstrike and just like demolish a whole area of tissue? And what I'm proposing is that if that's how we ask the question, instead of counting IgGs, if we look at antibodies by which type of immune response they are going to elicit, that we can use that to build illness trajectory maps. And so this is the concept that I call predictive diagnostics. And this is one of the main goals of my lab is let's try to identify very early in the infection which way you're going, because not only could that then be a diagnostic to distinguish long COVID from recovered, but way earlier in, when we know which way you're headed, maybe we could prevent you from even going down that road. And maybe we could intervene earlier before so much damage has already been done that then has to be repaired and restored.
To study that, does it require you to therefore look at people in active infection?
It requires us to compare. So in our Maestro study, we compare long COVID and chronic Lyme. That lets us look at these different infections much farther out. But we also have our acute Lyme cohort. And this is where our acute Lyme cohort is priceless. And if anybody here thinks this has acute Lyme in the Boston area, please come our way this summer, because this is priceless, because we can capture people in that moment of that acute infection before we know which way they're headed. And we can make a prediction in a black box envelope that we open later and we say, okay, were we right? Could we, in a perspective way, could we have said early in your infection, based on the features that you had at that time, which way you were headed? And that then has so much implications for us. And we are trying to work together with the Long COVID Recover initiative, where they also collected samples from people early in their COVID infection and then followed them out later. And so we're trying to do these things in parallel for Lyme and for COVID. And we hope that if we can build this as a platform, ideally then we'd be able to look at things like strep and other bacteria, other viruses or fungi that cause much pain down the road that we have not really been studying in this way or thinking about. You have diagnostics that have this capability currently clinically.
It's amazing.
Well, thank you.
And if you see that there's the airstrike activated instead of the SWAT team activated, does that then suggest that there is collateral damage that's caused by the immune system at that point, and that's the sort of indication that you may go on to develop an ongoing situation?
That's exactly right. And when I talk about macrophages, I talk about SWAT team. And when I talk about mast cells, I'm talking about an airstrike, because mast cells are going to trigger a cooperative response to remodel the tissue in a way that is going to cost you in some real collateral damage. But they can be tamed, and there's a way to tame them. And that would be very different than what would need to be done if you're just calling in the SWAT team. So these are really important to identify, and they have really, really important implications for treatment.
I love your personification of it as well, because it actually really, really makes it is, as someone who is not medically trained, sometimes these conversations, what I'm trying to do is distill your knowledge for an audience of people who probably have similar medical insight to me. So to have that kind of descriptor is really, really helpful.
I'm glad. I'm really glad.
You have actually mentioned multiple of the, well, I spoke to Akiko Iwasaki way back in about 2021,
my PhD advisor,
who you studied under. And you've actually mentioned the 4 things that she felt early on, where we were talking about the autoimmunity, the viral persistence, the viral reactivation, microclots. And then when I was doing my research for this today, I found that you together, I don't know if this was when you were still studying with her, had looked at the role of mitochondria. Back in 2011, you'd done a paper together. And so that's just one further sort of cellular function that I wanted to talk to you about today, because it does seem to be, now that we've touched on the macrophages and the mast cells, the mitochondria does seem to be something that has been raised as a potential, I think it's raised as both, isn't it? As a cause and an effect in multiple of these conditions. What have you found in these infection-associated conditions has happened to the mitochondria, or what role do you think that the mitochondria are playing?
First of all, I want to say, really glad you picked up on, clearly Akiko has been extremely influential in my thinking. She trained me, and just the approach in which I take to think about even how to conceptualize this is very clearly inspired by her. While I was doing my PhD with her, we engaged another faculty who studies mitochondrial biology, Jerry Shadell, who really helped us on that project, where what I was doing as part of my PhD work is that I was trying to understand these connections between how we clear our trash. So if you like these personifications, I want you to visualize that, let's say you have gathered all of your recycling, but it didn't just disappear. You still have to take it out. So somebody still has to take out the trash. Somebody then has to get that trash taken care of, or the recycling, and recycle it. And so you have these same components and processes are needing to happen in your cell. You need to trash some things, you need to recycle some things, but it's not just enough that you targeted something for clearance. That clearance actually has to happen. The recycling has to happen. Again, there's a lot of things that can go wrong. A lot of things need to happen perfectly. And your mitochondria are really central in that they make life or death decisions for the cell. And you have entrusted them to do that. And while they were once originally free-living organisms of their own, they have long since been held hostage by us, and they fuel our cells. And in exchange, we make a lot of their proteins. But to get proteins into the mitochondria, we have to unfold them. Now, if you're having a viral infection and you have all these unfolded proteins and you have no other way to clear them, one thing you might do is stuff them in your mitochondria. Maybe there's a couple of reasons for this. Maybe you want to get some more food into the mitochondria, or maybe you want to get the mitochondria to clear them for you. But at the moment that you need all this energy and all this help from your mitochondria, you're not always actively helping them. At the same time, they're generating a tremendous amount of heat. And one thing I really wish we thought about more in the context of immune responses was temperature. I'm like begging, literally, anybody listening, think about temperature, because we know we fever to fuel different immune functions. Different immune proteins function differently at different temperatures. Your mitochondria get really, really hot. And there's a really important gradient there and a really important impact on different protein functions. And so one of the things I was doing in my PhD was trying to understand how a problem in recycling of damaged mitochondria was really, really, really impacting your ability to respond to RNA viruses. And what's really funny, you might laugh now, is that at the time when I was doing this work, I thought I was doing such basic science, and I was just dreaming of doing translational science that was going to be impactful for humans. And then I transitioned in my postdoc. I worked with Irv Weissman, and I was co-mentored by Kim Hassenkrug at NIH, but I was at Stanford with Irv Weissman, and I was looking at immune regulation and these immune checkpoints, which are in place so that your immune system doesn't kill you when it's trying to respond to an infection. There's limits, there's breaks that are set on this response. And so I had transitioned to this field because I thought that would be so much more impactful. And then there was a worldwide pandemic of an RNA virus that was impacting everybody's mitochondria. Suddenly I realized that my PhD work wasn't such basic science after all. And I think one thing I really hope people understand is that when we make funding decisions about what is or is not going to be important, we never know what basic science we're going to need. You never know in advance what foundational scientific concepts are going to be critical for understanding disease processes that you're trying to understand until you uncover them. And so actually, I think in the end, it turns out that very little of basic science is actually truly basic and not ends up later being realized that it's foundational for understanding disease mechanisms, even if you didn't know how to pitch it to a particular disease at the time you were doing the research. But I definitely learned that from myself. And I have circled back to the mitochondria. I was just at a big mitochondria conference, entering back into this world saying, I've been gone too long, but I need to reconnect with you all. And I need to think about how the mitochondria are so key here and what's going wrong, because fuel isn't limiting. The mitochondria have fuel. So why aren't they? What's the dysfunction? And there's a lot of different ways to think about mitochondrial dysfunction. And there's different things that could be going wrong. And one thing to think about is that mitochondria let's think they can spin this way and they can use molecules to produce energy, right? They can break down sugar and produce energy, or they could spin this way and they could use energy to produce important molecules that you need to build things. And I think there's so many foundational things we need to understand in terms of what's happening to the mitochondria in these energy-limiting illnesses and in extreme fatigue and in chronic illness. But I think one of the things we have to understand is, are they even spinning the right way? And when we think about these biochemical cycles, biochemistry cycles, and we think about the TCA, a Krebs cycle, as you might have heard of it back in biochemistry, it really matters which way you're driving it. If the virus is hijacking things to try to, or a bacteria to try to get you to make stuff for it and use energy, well, that might be exhausting. And we need to get down to that level of what is happening. Why are the mitochondria getting damaged? Why are they not producing the energy they need to produce? And we have to understand it in the context of all these other things. You're also not, maybe your sleep is impacted, and maybe you're not getting restorative sleep, and maybe there's immune processes underlying that. But then at the end of the day, you're not going to do the things you normally need to do during your deep sleep to wake up feeling refreshed and rejuvenated.
And to clear out the recycling.
Yeah. Did anybody take out the trash while you were sleeping?
Yeah.
Yeah.
Is it something that sort of mitochondrial dysfunction, is it something that is prevalent across all of the conditions that you look at?
This is something we need to understand. What's clearly going wrong is there's clearly something wrong with people's energy levels when people feel that. And then if we take that back to the base currency of energy in the cell and the mitochondrial output, that's where we need to really try to understand, is the mitochondria outputting enough? Is it just that you have so much inflammation going on, so much immune attack that you're using so much energy? Maybe you're making enough, but you're using so much. It's like you're running a marathon and that's why you feel exhausted. Or is something wrong with the output? Are you actively damaging your mitochondria? And there's many, many different ways that an immune response can lead to damaged mitochondria. But remember, these were once foreign entities. And if you open them up, you'd see features that are found in bacteria, and that's going to be a problem. If you start directing your immune attack to those features. So there's a lot that we need to understand, which unfortunately most people would think about as kind of basic science research that's missing here. And that needs to be done for us to put these pieces together. And that's something I would love to do if only there was time and money, right?
Yeah, I think the money is a challenge for so many of the people that I have spoken to in terms of maintaining research funding. But I think given what you're currently studying, I think that time might be the thing that limits you.
Oh my God, I feel like Maestro is this. I feel like I just feed Maestro hand to mouth, all the money.
But it's remarkable what you're doing. We didn't even get to
the gynepathology story,
really deep dive into some of it or get to further on. But I don't want to keep you longer today. I am going to have a conversation with Beth at some stage as well, so I can pick up on some of those things. When are you anticipating that you will fulfill the quota for Maestro in terms of people?
The end of 2025. This is the year that we finish. Yeah.
Okay. And what's the length of time over which you look at everyone?
So most of the people who participate in Maestro will just be coming in the once. The people who come in for our acute Lyme cohort, those are the people who are getting followed. And then we match controls for them from our other cohorts. So people who participate in Maestro, we may end up contacting them and asking them if they would come in again and again. To match our acute cohort. But the structure is that it's really the acute cohort that is getting followed longitudinally.
So they're the ones that will require the largest time
commitment
to be followed, but the other people just come in at the one time point.
That's right.
But with multiple, you have a as you mentioned, the pre-questionnaire, but is it a pre-interview that you do before they come in?
Yeah, and they need to consent. And so that all happens in advance, where they hear about everything that's part of the study and see if they consent to that. And then we schedule them and bring them in.
Are you still looking for people in the Boston area if anyone listening might be interested?
We are, though I have to say these communities are incredible. And the chronic Lyme and the long COVID community have just reached out with such incredible. I mean, when our study went online, the chronic Lyme cohort was already oversubscribed. That's not to say don't try to enroll. Please do try to enroll, because the important part of the study is that we have to carefully match, females, males of particular ages. And so while we may have more people who want to participate than we can take, you need that in order to be able to find just the right people so that our cohorts are perfectly matched. But it's the acute Lyme. If anybody hearing this gets acute Lyme anytime
enroll
in 2025, please enroll. Yeah.
I mean, I will fly to Boston to be part of that study, but I suspect that I am the demographic that you already have oversubscribed in terms of the long COVID, which is female, 40s, white.
Which also tells us a lot. And one of the things that we have wanted to do is find a way to reach back out to everybody who contacted us with a simpler version of the questionnaire to even just collect these demographics there's so many things that we can learn even just from our surveys. That's something that we would like to.
When you're doing the Maestro study, you have huge, amazing AI learning capabilities, do you? That collate things
collaborate. So we collaborate with a lab at MIT. Doug Laufenberger's lab is just really amazing at building these computational models. And we also collaborate with a company called Alden Scientific. Using AI to understand biological networks is what they do. And so with those two really key collaborators, we're able to get a lot of insight out of all the different things that we're trying to look at.
And then what a time to be doing it. The fact that I know that we have a lot of criticism in our world for our kids being on devices and things, but the ability for you to collate this information that you're gathering from so many people and be able to produce helpful models from it is quite remarkable. Thank you so much for your time today, Mickey. I really, really appreciate it.
Yeah. We're really hoping that we're going to be able to help and make a difference here in this big problem.
I'm fascinated by this potential crossover with connective tissue disorders, with endometriosis, these comorbidities that are coming into this fold and developing our understanding of the human body and particularly the female body. I really welcome this approach that is being repeated by many of the experts to whom I get to speak, that we need to consider the varying forms, time and infiltration points and our genetics in the way that these pathogens impact, and apply our existing knowledge to give us a fuller understanding of how and why some people have long-lasting effects.
Thank you for listening to Make Visible. Please do like, follow, or subscribe to listen to our next episode where we'll be uncovering more insights into complex chronic illness. This was brought to you by the team at Visible, a group of scientists and engineers whose lives have been affected by energy-limiting health conditions. We're building wearable technology that's helping 100,000 people measure and manage their complex chronic illness. To find out more about what we're working on and how Visible could help you, visit our website at makevisible.com.